Good morning, everybody. I would like to welcome you to the ECE Department Colloquium. This is a bit of a first for us. This will be the first in-person colloquium, as far as I'm aware, in 2 years. So we're pretty excited about actually being able to meet again in person. One announcement that I want to make to the 491 500 students. We will be taking attendance. I have a sheet, probably about 15 minutes in. We just pass it around. Just put your name and net ID number in there, and you'll be fine. Okay, so today we have actually a very special speaker that comes to us from Dallas, Texas. She works for Texas Instruments. We're in the connectivity group, and she's actually a TI fellow. She received her BS and MS degrees from the Massachusetts Institute of Technology. And I'm not going to just sit here and rattle off her bio, but I'll just say some notable achievements. She's very active in the IEEE. She's been on the RFIC committee, Radio Frequency Integrated Circuits Symposium. She is currently on the International Solid State Circuits Conference Technical Program Committee. And she is currently an associate editor for the Journal of Solid State Circuits, which is really the most prestigious journal in the solid state circuits community. She's also serving as a distinguished lecturer for the Society. And she's going to talk, I think she has a very exciting talk today about the Internet of Things. And so with that, I'd like to introduce Danielle Griffith, and you can take it away.
Thank you for that introduction. So the title of my talk today is Crystal-Free Wireless Nodes for Next Generation IoT. So the outline of my talk is as follows. First, we're going to look at the Internet of Things market forecast, and then some of the characteristics for wireless nodes for IoT applications. And based on this, we're going to see what motivations and advantages there might be to removing the crystals in these wireless nodes. So many nodes require two crystals, a higher frequency one in the megahertz range, which can be replaced, as we'll see, with bulk acoustic wave resonators. We'll look at the design, compensation, and clock architecture for these. The second crystal that we want to remove is low frequency at 32 kilohertz usually, and is used for implementing a sleep timer. So we'll talk about what a sleep timer is, what the specifications are, look at some oscillator architectures and required calibrations. And then we will end with the conclusions and an example of a crystalless wireless node. So this slide shows the global IoT market forecast in billions of devices from the market research firm IoT Analytics. It's between the years 2015 and 2025. And we see that the growth rate was 26% per year between 2015 and 2020, and it's projected to be 22% over the next few years. You probably can't read the fine print in this projection, but it's interesting to note that it says it's counting gateways that concentrate end node sensors, not every sensor. In other words, the number of connected radios is going to be much higher than the forecast of 27 billion, which is on this graph, perhaps very much higher. And also, we should look and note here that the curve shows no signs of leveling out beyond 2025. And if anything, the growth rate just seems to be increasing. So the applications for low-power wireless connectivity are very broad, and they're constantly growing, and that's what I find so exciting about the field. Just a few examples include wearables, building and home automation, automotive, smart grid and infrastructure, and many more. However, despite being such a broad and growing market, there are many core requirements that apply to all of these devices. First, they need to be very low power. Most of the applications are battery powered, and often the battery lifetime either has to be several years or the lifetime of the device. And because of this, according to the Bluetooth Low Energy Special Interest Group, for example, there were 4.6 billion BLE devices shipped in just 2020, with an increasing number projected for future years. And this is just one small portion of the IoT market. So we can see that it's not realistic to change or charge tens or hundreds of billions of batteries a year, unless we're going to have a whole new career of people who just change batteries and nothing else. And next, all of these wireless nodes need to be very low cost. Sensor networks can have hundreds or thousands of end nodes. So the lower the cost, the more nodes can be deployed and the more data that can be collected. Small size is also important because it enables new applications that today yet we're not thinking about. And of course, security is very important because as these nodes are deployed into new applications and new markets, we want to be sure that the data they collect is not compromised. And finally, the Internet of Things is growing in industrial and infrastructure applications, which have more challenging requirements in terms of robustness. So now let's look more into the wireless node size limitations. In the picture on the right, a wireless SoC is shown on top of a US quarter. The radio requires 2 crystal oscillators to operate. So the first one is typically between 12 and 60 megahertz, and this generates the reference clock used in the RF synthesizer for the radio, for the receiver and the transmitter. The accuracy required to meet, for example, the Bluetooth Low Energy standard is plus minus 50 parts per million, while for other standards, such as a lot of those used in the sub-1 gigahertz space, the accuracy requirement is more like plus minus 20 parts per million. The second crystal shown here resonates at 32 kilohertz, and it's used for synchronizing data transmission between the nodes. These nodes are duty cycled to reduce power consumption because they're battery powered, often. And because this clock is always enabled, it needs to have a current or a power consumption that's very low, typically under a microamp current draw from the battery. And this oscillator, due to just the crystal behavior, tends to be accurate to better than plus minus 500 parts per million. And so we can see here in this picture that these 2 crystals are really very large compared to the IC with the radio, the memory, and the rest of the node. So we're very motivated to get rid of them to reduce the size and enable new applications. So on the previous side, we saw that the crystals are quite large, but they're not the only components needed for implementing the wireless node. Inductors and capacitors are also needed. These are used for implementing the RF matching network, the power management, maybe a DC-DC converter, and supply decoupling. An example schematic for this is shown on the right. But if we look at the cost of the components, we can see that the crystals are by far the most expensive components in this wireless node. So in large volumes, the crystals themselves can cost around 20 cents, which is more than everything else, and it's even more than the cost of the battery in most cases. So a cost as well as size is another reason that we would like to get rid of these crystals. So in an effort to reduce both the cost and the size of the wireless node, we have to also support the smallest battery size possible. So on this plot, we can see that the average current consumption of a wireless node is plotted versus the desired lifetime in hours for 5 different types of batteries. 3 coin cells, a AAA battery, and an iPhone battery. So we could see that if we want a 2-year battery lifetime using the largest of the coin cells, the CR2032, which is very common, we can see that the average current drawn from the battery needs to be no more than 10 microamps. If we want a longer lifetime, for example, 10 years, so that we never have to change this battery the entire time we have the device in operation, then the average current draw needs to be somewhere between 340 nanoamps to 13 microamps, depending on what type of battery we're using. So from this plot, we can see that a low-cost, small-size solution requires very low current consumption. Now, in many IoT applications, the data throughput requirements are much lower than the wireless channel bandwidth. This means that we can use duty cycling to reduce the average current consumption. So an example of that is shown on the right on the plot. So at the top, the current profile versus time is shown. You can see that the wireless node draws, in this example, around a microamp while it's in standby or sleep. And then every now and then, it wakes up and draws, in this example, 5 milliamps from the battery while it does a radio event. And then it goes back to sleep again. So at the bottom, you can see a zoomed-in view of one of the active periods, which we'll talk about in more detail later. And so during the standby period, a sleep timer, usually a 32 kilohertz crystal oscillator that I mentioned earlier, it's running, and it triggers the wake up of the radio at the right time for synchronized data transmission. So 32 kilohertz is often used because the oscillator needs to be very low current consumption to operate, and only a small portion of the total 1 microamp current budget during standby. So the average current consumption is a function of both the standby current, which is the sum of the leakage current, memory retention, 32 kilohertz sleep clock, and power management, and the PMU efficiency, CPU active current, receiver and transmitter currents, and currents used by any sensors or peripherals, and finally the duty cycle, or just how often the device wakes up. So in addition to low power, small size, and low cost, wireless nodes also need to be robust against attack, and this is only becoming more and more important over time. So security usually brings to mind data encryption requirements, and you'll see ICs that use AES 128-bit security. They have random number generators, firewalls, and all sorts of other security measures. However, even with all of these fancy techniques, ICs can be compromised by glitching the clock. So let's look at an example of that here. In the green box on the top, we can see the intended operation. So at the first clock cycle, an instruction is loaded into the CPU. And at the second clock cycle, another instruction is loaded, and the first instruction executes. And then on the third clock cycle, a third instruction is loaded, and the second one is executes, and so on. Now let's assume, though, that we're using a crystal oscillator, because they are used in all of these radios. And here, the first instruction is loaded into the CPU. And then on the next clock cycle, or actually which is a glitch, the second instruction is loaded, and the first one starts to execute. But it doesn't finish because the actual clock cycle starts, that it isn't the one that's after the glitch. And the first has no time to finish executing. So whatever that instruction was, whether it was a password check or a security check or whatever other security that was needed, whatever critical thing happened, it just didn't happen, and the security is bypassed. So this is a real problem. This can happen. You can try to do this yourself. You can search for Chip Whisperer, and you'll get a tutorial on how to do this with commercially available devices out there. So the solution here is that we can't use crystal oscillators because of security concerns. They open up the security of the device and allow it to be hacked much more easily than otherwise. So yet again, we want fully integrated clock source, and we want to get rid of the crystals. Okay, now let's talk about crystal oscillators in more detail. A crystal, together with active circuitry, is which contains a sustaining amplifier, form a crystal oscillator. There are several advantages of crystal oscillators, which is why they're always used. First, it's a mature technology, significantly predating integrated circuits. The first crystal oscillator was 100 years old last year, and even though that technology is so old, papers are still getting published about it nearly every year in ISSCC, the premier circuits conference. So next, the crystal has a really high quality factor, typically greater than 30,000, which has two advantages. First, it means we can have very low power consumption for the oscillator, typically around 10 microwatt per megahertz for commercial designs. And next, it has a very stable oscillation frequency, stable to under 100 parts per million, or 0.01% variation over an industrial temperature range. But despite these advantages, there are disadvantages, of course, because we want to get rid of them. First is cost. As mentioned, they're quite expensive. It's equivalent to 1 to 2 square millimeters of silicon. In other words, this one passive component is equivalent to 20 million transistors in 16 nanometer FinFET. So very, very expensive. The most common size today is 2 by 1.6 millimeters squared, so that limits the size of your wireless node. And next, the frequency accuracy, although it's good, it's not great at the temperature extremes. You can see that on the plot shown here. At the temperature extremes, it starts degrading quite rapidly, which is a bit of a problem in some applications such as automotive. Also, because of this high Q, it has a relatively low startup time, or long startup time, which means that the startup energy can be a limiting factor in duty cycled applications. It's also sensitive to shock and vibration, which is a problem in industrial environments. We see these components fail in certain applications. And what's become even more of a problem lately is supply issues. When I first made this slide, I wrote that a 12 to 26 week lead time was common. In other words, a customer places an order and half a year later they get their parts. In today's environment, this is good. They don't get them in half a year later. It's longer than that now. So there are so many reasons that we would like to remove the crystals from the wireless nodes. So one alternative to crystal oscillators is bulk acoustic wave resonators, or BAW. These are passive devices consisting of a piezoelectric material surrounded by electrodes. So piezoelectric just means that energy is converted between electrical and mechanical energy. And it also means that the mechanical resonant behavior is in the bulk of the material versus SAW, which you've probably heard about, which is surface acoustic wave resonators. So aluminum nitride is the most commonly used thin film material for BAW resonators. The resonance frequency, FR, is proportional to the film thickness and the acoustic velocity. In other words, to increase the resonance frequency, the film has to become thinner. And it also means that the possible BAW frequencies we can have are set by thin film manufacturing capability. It's not just a matter of, like we do in circuit design, of drawing a different layout. It has to do with the manufacturing thickness. So BAW and SAW resonators are used extensively in filter products. And every phone probably has 20 BAW or SAW filters inside of it. So although billions of BAW and SAW devices have been manufactured for use as filters, they haven't been used so often to create oscillators. The first BAW oscillator was published in 1976, but it wasn't released as a commercial product until 2019. So the first two types of BAW resonators released to the market are shown here. First, there is FBAR, or thin film bulk acoustic wave resonators. This is the one shown on the left here. These are used in Broadcom's filter products. They're manufactured with electrodes on either side of the piezoelectric layer and an air gap underneath of it, as shown here and on top. The air gap helps to increase the quality factor because the energy doesn't leak as easily into the substrate. The second type is solidly mounted resonator, or SMR. These are from Qorvo's RF filter and duplexer products. Here there is an acoustic mirror that's shown here underneath the resonator that keeps the energy out of the substrate and up in the piezoelectric layer where it belongs. In either case, these resonators can be sensitive to external forces, and they might require hermetic packaging and air cavities to isolate them from the outside world. So in 2019, TI introduced the third type of BAW resonator to the market, called a dual Bragg BAW resonator, shown here. Bragg reflectors, or mirrors, are structures with alternating high and low acoustic impedances that keep the energy reflected back into the piezoelectric film. And the better the mirrors are, the less energy leaks out and the higher the Q. The Bragg reflectors also prevent contamination, so the frequency drift versus time is very low, and then the frequency is very stable. So the total thickness of these resonators is about 5 microns, as shown in the cross-section at the upper right. And in the lower right, you can see a side view of them where the BAW resonator has been placed on top of a silicon die and wire bonded to it. The irregular shape, maybe you notice here, this is optimized to reduce spurious resonance modes, and the resonance frequency is around 2.5 gigahertz. Now let's move on and talk about temperature compensation. Many of the materials used in MEMS devices soften and expand as temperature increases. This is quantified by a parameter called Young's modulus. So aluminum nitride has a negative temperature coefficient of frequency, as shown by the red line in the plot here. Whereas silicon dioxide, on the other hand, has a strong positive temperature coefficient. So what we do for temperature compensation is just adding a thin layer of silicon dioxide so that the blue line and the red line cancel out as much as possible, and you're left with what's shown as the green line here, the composite behavior. However, it's important to note that this green line, if we zoom in, is actually going to have a parabolic second order temperature coefficient that might be left over after you do the compensation. And here we are, we've zoomed in on the plot a little bit more. So without any passive temperature compensation, aluminum nitride will have more than 3,000 parts per million shift in the resonance frequency over the industrial temperature range. That's corresponding to the black line in the graph here. So that's fine for filter applications, which is why these resonators have been used in filters for so long. But it's not sufficient for clocking applications. So as mentioned, we add in a silicon dioxide layer with a positive temperature coefficient, which means it becomes mechanically stiff at high temperature. And if we can add it with a perfectly controlled layer thickness, then we can get a composite temperature coefficient of frequency of around 0.5 parts per million per degree C. That's very much like a crystal oscillator. That's fantastic. However, we can't precisely control the film thickness. So in high volume manufacturing, we actually end up somewhere between these red curve and the blue curve. So you can see as the different film thickness changes here, we get a different slope of frequency versus temperature. So this gives us less than 300 parts per million frequency variation over a wide temperature range. which is good, but it's still not quite good enough for a lot of communication applications. So we started off with a completely uncompensated resonator with 3,000 parts per million frequency shift. We add in the passive temperature compensation, which takes us to around 300 parts per million. And then on top of that, we combine it with active temperature compensation. So then active plus passive temperature compensation gets us down to around 20 parts per million frequency shift over temperature. And that's done as shown in this diagram here, where we have a temperature sensor and a lookup table, and we provide some sort of temperature correction to our oscillator. And 20 parts per million is an example. Of course, you can imagine that how accurate it's going to end up being is actually just a function of your temperature sensor accuracy and how often you do the compensation. Do you do this continuously or only every once in a while? So when we have crystal oscillators, temperature sensors often get implemented as a resistor inside of the crystal oscillator with a purposefully high temperature coefficient. You measure the resistor and it gives you an indication of what the temperature is. For the BAW technology though, it's actually a really nice idea. And what you can do is to have two BAW oscillators, one without the passive temperature compensation and one with, shown as BAW 1 and BAW 2 on this slide here. So then you use a counter to compare the relative difference in these two frequencies, and it gives you an indication of what the temperature is, because the temperature is proportional to the frequency of BAW 2 minus the frequency of BAW 1. And the nice part of this idea is that you can get as accurate value as you want just by allowing the counter to measure for a longer time. But of course, you need to do some sort of initial offset calibration in production. And this slide shows how the active frequency compensation is actually implemented as an example inside of a 2.4 gigahertz ISM band radio. The BAW oscillator is down here. It has a fixed divider and it provides an uncompensated clock as a reference to the RF synthesizer, which is a PLL, and the modem. And then the frequency compensation value is generated with a temperature sensor and a stored parabolic curve fit, matching the equation up here. And the compensation value is provided to the RF synthesizer and it's corrected so that the output clocks from the radio are accurate to within 20 parts per million. In this particular example, it is sufficient to just apply the temperature compensation code whenever the temperature changes by more than 4 degrees C. So it doesn't have to happen very often in most applications. This slide shows measured results for the active temperature compensation described on the previous slide. The frequency error is plotted on the y-axis and the temperature on the x-axis. And the results are measured on 80 different devices at the output of the RF synthesizer, or the PA output, which is at 2.4 gigahertz. So any error in the reference clock then shows up directly at the RF output. So the red points are with the temperature compensation off. So we can see then just the passive temperature compensation from the resonator. And the green points are with the active temperature compensation enabled. And you can see here that we stay within 10 parts per million frequency error, which is easily within our spec window. So now that we've discussed the temperature compensation, let's move on to talk about the resonator model and the oscillator design. Just like the crystal, the BAW resonator can be modeled by a 4-component modified Butterworth-Van Dyke model topology, as shown down here in the corner. The resonator appears inductive between the series and parallel resonance frequencies, as shown over here. And the quality factor, the parallel quality factor QP, is the resonance frequency divided by the 3 dB bandwidth. So also important to note is that this BAW resonator, unlike a lot of other MEMS structures, has only 2 pins. No ground, no power, no bias voltage, just 2 pins. And it also it has a high impedance at DC, which means you can't just drop it into your existing VCO topology you already have. So although BAW oscillators weren't used in commercial products until recently, they've been published many times since the first one in 1976. Some of the architectures are shown here on this slide. On the left is a Colpitts oscillator published in 2007 by STM. So this topology is very commonly used and achieved about 600 ppm frequency variation, had a Q of 600, and a current consumption of 4.8 milliamps. In 2007, a differential architecture was published by University of Washington and used current source loads and frequency tuning and achieved about 600 microamp current consumption at 2.1 gigahertz in 130 nanometer CMOS. And finally, on the right, a complementary differential architecture from 2011 was used to achieve low phase noise with only 675 microwatts of power consumption at 2.5 gigahertz in 180 nanometer CMOS. There are a lot of other BAW papers out there, but these slides just show you an examples of the typical architectures and achievable results. Now let's look at the complementary differential structure in a little more detail. So on the schematic diagram to the right here, the oscillator is made by stacking a resonator on top of and wire bonding to the device, the transistors down below. We have a PMOS current source at top, providing a bias current. However, unlike a typical LC VCO that you might be familiar with, there are 4 modes possible for this BAW oscillator. First, the thing can latch instead of oscillate if these decoupling capacitors are too small. Then it can have a parasitic oscillation if the decoupling capacitors are too large compared to the load current. And there's a derivation in this paper here if you're interested in it. And the third one is the actual desired operation, where it's typically oscillating somewhere between 2 and 3 gigahertz, depending on your resonator. And finally, there's a 4th mode where there can be a parasitic oscillation at a frequency that I've called FB in this slide, which is a function of the bond wire inductance and the equivalent capacitance of the oscillator. So to avoid the parasitic oscillation, we want the bond wires to be very short, spaced as closely together as our packaging rules allow, and we need to be sure that we have no loop gain at this parasitic frequency. Of course, if we use flip chip packaging or an LC trap, we can remove the problem. But I think what we can take out of this slide then is that this is not the same sort of oscillator topology in the end that you would have with an LC VCO that you might be familiar with. So another consideration for a new type of frequency reference is how it performs in harsh environments. This is really a common problem with crystal oscillators, and I talk to a lot of customers who have problems here. So what we've done here is test the BAW resonator under mechanical shock according to this military standard 883H, which involves a peak acceleration of 1500 G and with a pulse duration of 500 microseconds on 3 different axes with repeated shocks. So even though it says military standard, it doesn't mean it's only used by the military. This is used very commonly to do a lot of testing for crystal oscillators in industrial environments. So we have, and then you can see the test setup that we're measuring here. We're keeping the oscillator together with the radio enabled and transmitting and receiving during these tests. This slide shows the result. So the SOC frequency is measured using the BAW on the left in green, and we're plotting the instantaneous frequency on the y-axis versus time on the x-axis. And so we can see that if a radio were operating with a protocol that had a very narrow RF bandwidth, the RF signal would be transmitted at the wrong frequency when the shock happened, if this variation is too large. And we can see that the BAW shows 4x better shock immunity than the crystal does. In other words, up to 2 ppm versus 8 ppm frequency error. And that's really purely because the BAW resonator has a lot less mass than the crystal oscillator. So we're taking advantage of the integration and the scaling and the smaller size and getting an advantage in terms of robustness for harsh environments. And this is important in terms of like factory monitoring applications, power tools, smart golf balls, or other applications like that. So a final advantage to mention with BAW oscillators versus crystals is a lower startup energy. The current profile is shown here for radioactivity again. So this is a little more cartoon figure compared to the measurements we showed before. The BAW resonator has a Q that's roughly 10x lower than the crystal, and it's about at 100x higher frequency. So we would expect the startup time to be about 1,000x faster, all else being equal. And what we see here is that that is the case. We get, even including some overhead for clock qualification, we get a much faster BAW oscillator startup time. So we spend less time waiting for that crystal oscillator to turn on. It turns on much faster, and so there's less energy wasted. So this red area here is just wasted energy, wasted startup energy, which is much lower for the BAW oscillator, which means we can get a net savings. So not only are we smaller size, lower cost, more robust, we're also lower energy. So now that we've seen that the BAW resonator can be an effective replacement for the megahertz crystals in a wireless node, now let's move on to that second crystal we want to get rid of. So as we discussed earlier, in many IoT applications, the data throughput requirements are really low. Maybe we're only transmitting data every few seconds or minutes or so on. So to save power, the radio is duty cycled aggressively. And maybe it's only on, the radio's only on like 0.001% or up to 1% of the time. And the rest of the time it's in a low power sleep state. But how does it know when to wake up? We know when to wake up by using a low power sleep timer to synchronize all of the devices so that they're all only awake just when they need to be. Except that we're not perfectly accurate in this clock. So there is a region under this curve called the guard time. What we're doing here is the radio has to wake up, assuming that the error is the worst possible, worst case assumption for the frequency error. And then it has to turn on and just listen to be sure that it gets the incoming packet if the errors are the worst. So the less accurate your sleep timer is, the more time it spends in this guard area here, which is the red area under the curve. And it's just basically wasted energy there. So you might ask, how important is this sleep timer accuracy? But that depends on the wireless node duty cycle. We show just a simple example of that in the slide here. We're looking at the average power consumption of the node on the y-axis versus the duty cycle on the x-axis. We're waking either after minutes on the left or waking after milliseconds on the right. And it's been calculated with different sleep timer accuracies between 1 ppm, which is not realistic, up to 1,000 ppm, which is a very loose spec. And we can see that if we're going to be sleeping for a long time, which we think that we will be in many applications because we have to reduce our average power consumption, then we need a sleep timer or an oscillator that's accurate to around 1,000 ppm, I'm sorry, 100 ppm or better, so that we're not limiting that average power consumption. We want to be down into just a microamp or so range. So our goal is to remove the 32 kilohertz crystal oscillator. An obvious choice for this is, for a replacement, is an integrated 32 kilohertz oscillator based on an RC time constant. However, RC oscillator frequency variation over process voltage and temperature tends to be far beyond 1,000 ppm, shown in the previous slide, which is the upper limit for a lot of protocols. We do have that accurate clock in the system, though, the BAW that we've just added, which we know can be accurate to 20 ppm or so when we do our calibrations. Whoops. So usually temperature changes not that often. So what we can do is use a temperature sensor to trigger a periodic recalibration of that internal 32 kilohertz oscillator, comparing it to our higher frequency oscillator periodically. And the stability of this 32 kilohertz integrated oscillator determines on how often it has to be recalibrated. So if we do some analysis here, we end up finding out that we need typical specs of having, for this 32 kilohertz oscillator, of having a temperature sensor under 50 ppm per degree C. We'd like a supply sensitivity of less than 0.1% per volt. We want a long-term stability of maybe 10 parts per million over a second averaging time. And we want a low current consumption of under 200 nanoamps. So this slide shows an example of a commonly used integrated RC oscillator. Two currents are provided to a resistor and a capacitor. When the capacitor voltage reaches the voltage across the resistor, the comparator trips, resets the circuit, and the next cycle starts. In this case, the frequency is sensitive to current mismatch, comparator offset, comparator delay, and RC variation, all of which can change over temperature. To improve the frequency stability, chopping was added to this oscillator, which cancels the offset and mismatch and gets much better stability, but you're still left with changes in delay variation and variation in the resistor and capacitor. Target measured results were 120 nanowatts at 18 kilohertz, which is very good. Here you can see the measured results from the oscillator with the offset cancellation. We can see we get a 7x reduction in frequency variation versus temperature with the offset cancellation, which means that when you do this offset cancellation, you have lower power because you don't have to recalibrate your oscillator so often. Here's another example of an integrated oscillator. This oscillator charges and discharges the capacitor through the resistor, and the frequency is sensitive to inverter delay and RC variation. But we can improve this one as well. We see that if we do a regulation to make the inverter delay track a self-biased inverter, the inverter delay becomes constant over temperature, reducing the frequency variation. And the results were 190 nanowatts and 32 kilohertz. The plot on the right here shows the frequency versus temperature measured for 5 parts after a one-time calibration, and frequency variation of plus minus 0.21% over more than 100-degree temperature range. This means that the recalibration could be done very infrequently and still maintain the 500 ppm frequency accuracy that most standards need. So in those two examples I showed you so far, the frequency stability was still a function of the resistor and the capacitor. Now, usually the metal capacitors have a low variation with temperature, but the resistors don't. So one option we can use to deal with that is making a composite structure with resistors having opposite temperature coefficients to create an approximately 0 temperature coefficient resistor. But this isn't possible in every process node. Whatever you're using, you may find that that's not compatible with the technology you have. So a nice solution to this is published in 2021. And here, switching resistors with different temperature coefficients based on a lookup table from a 2-point trim called the pulse density modulated resistors was able to achieve only 8 ppm per degree C at only 1 microwatt per megahertz. So this oscillator was designed at 32 megahertz, but the approach is very compatible with 32 kilohertz, and it's a very nice paper that I recommend you read if you get a chance. So frequency versus temperature, it's not the only stability parameter that we are interested in. Another one that we have to consider is Allen deviation. So the Allen variance is a statistical measurement of the instability of the oscillator, and it's 1/2 of the time average of the squares of the difference between the successive readings of the frequency deviation, sampled over an averaging period. So Allen deviation is the square root of this, and it's typically plotted versus the averaging time. And if this all sounds kind of complicated, don't worry. Really, the point here is that low Allen deviation means that the oscillator drift is predictable and the recalibration can be done very infrequently. High Allen deviation means that the oscillator varies a lot around a nominal point, and you have to do the recalibration more often, even when the temperature is not changing. Here we can see that first oscillator we talked about with the offset cancellation enabled versus disabled. And when the chopping was off, the Allen deviation floor was around 200 parts per million. And when it's turned on, it goes 10x down. So this is just basically because the chopping is reducing the flicker noise by 10x, making this oscillator more suitable for use as a sleep timer. So in the literature, you're going to see people talk about the Allen deviation floor. That's their metric of choice. That's nice, but it's not actually the most important one. What you really care about is how long do you have to do your recalibration? In other words, how long do you have to measure it to get an accurate, to get a number that's sufficiently accurate? You can imagine that if you've got an oscillator with no frequency variation, no jitter, you only need to measure 1 cycle and you've got a perfect calibration. On the other hand, if you've got high jitter, you've got to average over a lot longer time to get an accurate calibration. So an example of that is shown here. We have Allen deviation from 2 different oscillators. They both have the same power consumption and the same Allen deviation floor, roughly. But the blue curve requires calibration to be done for 1.5 milliseconds to get 100 ppm accuracy. But the oscillator with the red curve requires the calibration to be done for 40 milliseconds, which is a 300x longer time. So there's a big power. So, no, I'm sorry. You end up with a 300x longer time of your high frequency clock being enabled than it would have been enabled just at what the radio needed, which is a huge power penalty. So to put that into perspective, here's an example where the average current consumption is calculated for that wireless node we've been talking about. That has a radio event once every second, transmits a short data packet, and then this goes back to sleep. So when you're using that oscillator with the good Allen deviation, your average current draw from the battery is 7 microamp. But then if you use the other oscillator, your average current draw from the battery is 29 microamps. So in other words, your battery lifetime went from years to a few months. The moral of the story is don't just look at the Allen deviation floor, especially when you're publishing papers. Look at it at how long would you have to calibrate this oscillator to make it accurate enough for what you're trying to do. So now let's put everything we've talked about together. We can replace the megahertz crystal with a BAW oscillator and divider to generate the reference clock for the low power wireless node. Both passive and active temperature compensation are used, and so the radio can transmit and receive at the correct frequency. And then A low power 32 kilohertz integrated oscillator is used for the sleep timer instead of a crystal. And it's recalibrated to the BAW oscillator. In other words, we need no crystals for this wireless node, which gives us an advantage in terms of small size, low cost, and it's environmentally, and it's robust to environmental, harsh environmental situations. And it's also secure. Here are a few pictures showing you what this looks like. On the left, we see the BAW resonator on top of some ASICs and wire bonded. In the middle, it's with a Bluetooth low energy radio, and on the right, it's in a larger package. So the space saved by removing the crystals gives us the chance for more applications. Here we are using that space we've saved to put in more sensors in the same footprint. In this particular example, we've got optical, humidity, and temperature sensors, as well as an accelerometer and an energy harvester, all in the size of a US penny, and it can connect to the phone and transfer data and work even in harsh environments. So in conclusion, the growing IoT market requires low cost, small size, environmentally robust wireless nodes that also have to be secure against attacks. Many nodes have two crystals, one used to generate the RF reference clocks and one as a sleep timer. The higher frequency one can be replaced with a BAW resonator, which needs both active and passive temperature compensation, which we talked about in detail. Once that's used, it enables small size, low cost, improved frequency stability, especially at the temperature extremes. The low power 32 kilohertz crystal oscillator can be replaced by the integrated oscillator as long as it has sufficiently low Allen deviation and it's periodically recalibrated. So once we've done this, we end up with wireless nodes that are reduced size, cost, and improved security, all of which are going to help us enable the growth of the Internet of Things market. Thank you.
All right, thanks for that wonderful talk.
Thank you.
It was very interesting. So I'm hoping there's a lot of questions. If there's not, I actually have a lot myself. So questions? Yes.
So is the reason we don't use
You guys, a little bit louder.
Oh, sorry, yeah. So is the reason we don't use an integrated RC oscillator for the higher frequency clock due to variation with temperature?
So let me restate the question so it goes into the mic. Is the reason that we do not use an RC oscillator is due to temperature, the dependence of an RC oscillator on temperature dependence? Is that the question?
Yeah, I'm saying, well, why don't we use that for the high frequency clock as well?
Yeah.
Yeah, that's a really good question, and it really comes down to wireless standard requirements. All of the wireless standards out there require that you be accurate, you transmit at an accurate or receive at an accurate frequency, and how accurate is accurate enough depends on the standard, but it can be anywhere from 1 part per million to 50 parts per million. And your resistor-based oscillator isn't going to be that accurate in the end. You also can end up with some issues with phase noise degrading your radio performance, but maybe we could overcome that somehow. But it, in the end, comes down to the wireless standards.
Yeah, I noticed all the integrated oscillators, none of them had any inductors. Is that due to the size of the inductors, or why is that?
Okay, so the integrated oscillators, I guess, make sure I heard the question right. You said why they don't have any inductors?
Yeah.
Yeah, so the inductors will allow you to make an oscillator in the 1 gigahertz and up range. So the power consumption is going to be quite high. In a longer version of this talk, I did go through some examples of using oscillators with integrated inductors to try to replace the higher frequency clock. They don't quite get there of what we need with the best ones that are published. I think I've seen 100 to 200 ppm frequency variation for them, so they're not quite where we need. And then if you want to go to a lower frequency for them, the inductors get prohibitively large.
Yeah. It basically boils down to the Q, right?
Yes.
Of the L. The Q of the L in the integrated solution is just so poor versus some of these solutions that were presented in the talk today. Okay, good. Other questions? Okay, yes, Cole.
Is this technology ready to go to the market as a replacement for crystal resonators? And if not, what would have to be done before they're ready?
I didn't hear that.
Is this technology ready to go to production versus just as a replacement to crystal oscillators? Did I get
It
that
is in
correct?
production today, replacing crystals, yes. You can buy it today online.
Good. More questions. I actually had a question. So it seemed like a lot of work's been done on calibration and reducing the calibration time as much as possible. And so a couple questions in there. The calibration time sort of relative, how often does it happen? Does it happen every single time you fire up the radio? Do you go through a calibration routine? Or, does it happen relatively infrequently relative to the duty cycle of the radio itself?
Okay, so there are two oscillators that are being calibrated here. One is the BAW oscillator, where it's not actually being calibrated, it's just having a frequency trimming code applied based on the current temperature. So that's very quick. Just read the temperature sensor, apply the correct code, and go. For the integrated oscillator, where we're doing the calibration, there the optimum way to do it is, say, you only need to recalibrate when the temperature has changed so many degrees C, depending on how accurate your oscillator is, or you need to recalibrate after some amount of time has passed, usually like minutes, because of the Allen deviation.
I see. And so a lot of these applications, the duty cycle or the period between firing up the radio is well more than minutes, right? Could be hours, days, weeks, correct?
It can be, yes.
Yeah. And then actually along those lines, so a question actually I thought of is that, like in cellular applications, the settling time of the oscillator is sort of critical.
Yes.
Right? But that's more from a network capacity perspective rather than a power consumption perspective. So
Yes.
what I was wondering is, do people do a lot of work to reduce the settling time of the oscillator just to save the power, when you actually fire up the radio?
Yeah, so that's a good question. For most of these low power standards, unlike cellular, you don't need to be accurate to just very few ppm. It's good enough if it's accurate to 20 or 40 ppm. So the settling time is not really a concern. What you're talking about is more of a problem in standards like Sigfox, where you need a 1 ppm accuracy and the settling time does matter, especially
Gotcha.
like with self-heating with the PA or something.
Great. All right, any more questions? Yes, one more.
Yeah, it seems that all your calibration relies on a lookup table, but I was wondering if that lookup table actually gets updated with the aging information of the chip, or you actually don't take that into consideration.
The question's about aging, right?
Well, I don't know if you heard me before.
Yeah.
A little louder.
Yeah, it seems that all your calibration relies in a lookup table at the end.
Yes.
But I was wondering if that lookup table is actually updated regarding the aging of the chip.
Okay, yeah, that's a good question. That's a very good question. And again, that's in something that's a part of a longer presentation I have. I didn't have time to get through all of that today. For the BAW oscillator, the aging is very low, just a few ppm. So it's taken into account in all of the error budgeting. It's low enough that you never have to update that lookup table. But that's absolutely is a very good question. In really tight, demanding standards, either the aging, maybe it needs to come down, or you need to update the lookup table as the device ages. So, and that's often a thing that's not published in papers. You have to run these things in elevated temperatures for months or years at a time to see the aging. But you're right, you absolutely have to pay attention to that.
Okay, good. All right, so again, for the students at 491-500, the sign-in sheet probably was passed around. Isaiah, can you raise your hand? He's handling the attendance, so if you did not sign in, please talk to him on your way out. And let's thank our speaker one more time.